And the way I'll try to motivate it is by working out a simple one-dimensional example in which the dynamics is such that so the operation of flipping the axis to minus itself commutes with our dynamics. And as an example, I gave you this map. And it was a map, very simple linear map that had a property that I flip it this way and I flip the resulting map here. It's invariant under a flip. So the symmetry is dihedral group 1 or combinatorial group 2 or a symmetric group on 2 objects. Or, probably has more names, but basically just says there is identity element in the group and there is a reflection. And what reflection does, if you act on the function x, and the invariance is the usual statement that f of x. And this has a property that r squared is the identity. You reflect twice your back, so the inverse of r is same as r itself. So invariance is you start at x, you flip your initial, you apply your law of motion, and you flip it back, the inverse of r, and it's equivariant. So what kind of solutions, compact, short solutions we can have? A typical initial condition is ergodic. It just runs all over the place. But we obviously have 3 fixed points. So there is one I'll call C. The map has 3 branches, central one, right one, and left one. And that means that the world is partitioned by 3 symbols, left, center, right. And here is one fixed point. Then there is fixed point that stays in this upper corner. So this is R repeated forever. And this is left repeated forever. This solution is invariant under the symmetry. And as you'll see, also it has a special property that it's in the invariant subspace, which here it's very unimpressive. It's only 1 point, so you don't pay much attention to it. But in 100,000 dimensions, you will be more mindful of it. And then there's a pair of solutions here, which are related by the group action. Because if I flip this and flip that, that will go up there. So there is one fixed point with multiplicity 1, that's the one in center, and there are 2 fixed points, left and right, with multiplicity 2. But morally, we know they're the same because they're related by the symmetry. So anything we compute on the one should be the same as on the other one, even though in a full state space, they're sitting very far apart from each other. Let me draw a few more solutions. And clearly, I can find a 2-cycle that hops between left and right. So there is a 2-cycle which is left and right. XLR, XRL, and under dynamics it closes. And this cycle is G-symmetric. Because when we flip the whole thing, only thing that happens is the 2 points get exchanged, but the cycle doesn't get changed. So there's only one of those. So that's an example of a 2-cycle whose multiplicity is 1. then you can go on. This is a very easy thing because it has complete symbolic dynamics in 3 symbols. So you can just enumerate just by writing all possible strings of L, C's, and R's. You can enumerate everything. So there must be 2 more cycles. This is the one that hops between left and right, but there must be 2 cycles that hop between center and right and center and left. Go from center to the right and keep doing it. And then there is the one so this is go from the left to the center and back forever. So these cycles are asymmetric. I don't have a better word. But if you know a better word from group theory, let me know. Meaning that the symmetry maps them into each other, just like these 2 guys sit on the orbit. So it's a very simple system. All periodic orbits that you find will be either symmetric or asymmetric, meaning they appear in pairs. So multiplicity will be only 1 and 2. And for symmetric cycles, you can see that if you computed part of this trajectory, you know the rest, because this part is just a reflection of that one. So that one will have a prime cycle, half of the length of the full state space cycle, and these asymmetric ones will be the same length in the full state space and in symmetry reduced state space. So this is all totally easy. Now, if we divide the world into fundamental domain, so we take our state space and write it as fundamental domain union with fundamental domain multiplied by group element 1. So everybody who is D union fundamental domain multiplied by group element 2. And finally, fundamental domain is the last group element. Then we should be able to write the symmetry. So in the big space, the dynamics is described by some function f of x, which tells me where I get. In case of discrete time symmetry, this is in 1 unit of time, discrete time. But there must exist a corresponding thing that keeps me in the reduced state space. Fundamental domain, which is a quotient, which is just 1 bit of pizza. And for some reason, it's easier to draw this for billiards than for maps, but I'll refresh your memory how it looked for the maps. So this was full state space, and this is now symmetry reduced. So when we divide the state space into fundamental domain and the copy, we choose what to call fundamental domain. And in this case, clearly we'll just use a half interval. It's convenient to use half interval of the whole thing. And now the original map looked like this. So this part is just as it used to be. Let's start here. Original map said if I was close to this fixed point, this is how I got mapped. No problem. But then there's a part here that would map me in 1 iteration into negative part. So the group symmetry reduction says I should replace this by a reflected interval. So I should replace this by this. And, let me give them new names. And let me call this interval 0, 1, and 2. So, original map was up here. And the dynamics in reduced state space is obtained by, whenever you exit the positive quadrant, you just reflect. So this is the same dynamics, just in reduced state space. And it's the usual story. For some reason, it was easier to explain it in diffusion on one-dimensional chain. I just told you, whenever you went out, you just pull yourself back. This says whenever you come out, you reflect yourself back rather than translate yourself back. So it's very similar to what we did for diffusion, but this is now a map of on a unit interval being reduced to the map on half-unit interval. So now what I used to have here, everything that in a big space lands in these three quadrants of this figure has to be brought back by reflection. So there is an easy guy, this one, on the 2 interval, going forever, is the same fixed point as the right fixed point. So that one we're familiar. But then there was this fixed point, 2. Under reflection, it becomes this one. So while in the full state space, the orbit was of length 2 and had 2 points, in the reduced state space, it's of length half of that and has multiplicity 1. In reduced state space, everybody's going to have same multiplicity. So that takes care of this fixed point. Then in the full state space, we had this circle here, left to right. What does it look like in reduced state space? See, we start on the point of it. It's reflected point here, tuk tuk. And then as we go, we would like to go into this quadrant, but then we have to get reflected back. So the 2 cycle, left to right, becomes a fixed point, or relative fixed point 1 in reduced space. And it happens only once. So this had multiplicity 1, and now it gets written in terms of repeat of the relative prime cycle. Just half of that thing repeated twice. They had a part that belonged to here. So, this point will be reflected. And they had a part that belonged to this, but that gets reflected. So they become a cycle. So both the guy who is going from left and right, left to center and right to center, these 2 ones in full state space, because they are symmetric orbits, they don't get shorter in a state space. But 2 of them just become 1, which is called 0, 2, I guess. Yeah. This is branch 0, 1, 2, and this is hopping between 0, 2. So in this case, even though it's already looking a little bit confusing, only thing that can happen is that the original periodic orbit is still a periodic orbit, but because it was asymmetric, there was a group orbit of them, in which case just 2 copies, and now there is only 1 copy in the reduced state space. Or the orbit itself has a symmetry, like this one and any longer version that's symmetric under the double flip. And that one becomes an orbit of half of its length, or a relative prime orbit repeated twice. This branch had one slope, and these two branches had the other slope. And it was a symmetric looking map. The new map is asymmetric. I just drew it badly. Let me draw it a little bit more dramatically. So if the middle slope is very steep, then it looks like that. It has a branch which is very steep. That's this branch. And then it has two branches which have the same slope but opposite signs. And it doesn't look anything like the original map. It's desymmetrized. Dynamics in symmetry-reduced space has no symmetry. So there is no multiplicative operation that will get you from one to the other. It's a totally different looking map, and it's obtained by symmetry reduction. With some fortitude, you can work all this out, and you can agree with me.